Hello. So in this video, we're going to talk about glide planes. And glide planes are a variation on a theme, and that theme would be mirror reflections or mirror planes. So a glide plane is a mirror plane plus translation. So they are similar to screw axes. Screw axes are rotation plus translation. So glide planes are the case where we're using translation, moving a motif through some fixed distance, but combining that after a mirror plane reflection. So let's take a look at this. Let's say we've got a mirror plane here, and we'll draw a sideways tree. Not a very happy tree as in Bob Ross, but a sideways tree as best as we can do. So this is a simple mirror plane. We have a tree over here and we reflect it, and if I did a good job, then these would look exactly alike, except for one pointing to the left and the other pointing to the right. For a glide plane, we'd have a planar surface here, and here is our tree. Bob Ross would be ashamed, but we'd reflect it over to this side, but instead of stopping there, we would translate it some distance, and so our reflected tree would be over here. So we've gone some distance t, or usually in the translation terminology, we go to some distance t1 half instead of all the way out to where we would find another node. So the full distance t would be out here where the original tree laying on its side would repeat again. So that would be the full distance t. So this is a glide plane. But we're not going to call it g because we are going to be concerned with what direction that glide translation is happening in. So let's erase the chalkboard and go back to our sort of standard way of setting up crystal axes with A front to back, B left to right, C up and down. If that translation distance t1 half happens in the A direction, so let's say we're moving here, then that would be an A glide. So we can take that A axis, let's blow it up over here. Let's say our tree laying on its side was here, we reflect it and move it over here. So we're moving it along that A direction, and that would be an A glide. And you can imagine the same thing would work for designating a B or a C glide. If we're moving in the B direction, then it would be a B glide. And if we move in the C direction, then it would be a C glide. And we're not restricted to just moving along the axes. We can also move a T1 half direction that combines. Let's say we go half the distance along A2, but then also half the distance along C2. So we're ending up in a diagonal. So we can end up, if this is A, B, and C, that we end up going in some kind of direction here that's within the AC plane. So this would be referred to as a diagonal glide. Now you might think a perfect symbol for that would be the letter D, but we don't use that. We use the letter N because we're going to reserve the letter D for something else. So the diagonal glide is notated as an N. So how about the case for something that would be notated as D? Well, again, we'll draw the ABC, but instead of going half the distance, maybe we're just going 1/4 the distance. And it doesn't matter what combination. We could do something else here. Maybe it could be moving in the AB plane, but we can only go 1/4 of the distance relative to our unit cell. So it's A 1/4 plus B 1/4, and this would be a diamond glide. And we can move this 1/4 distance within any of the planes, the AB plane, the AC plane, etc. These would be designated as the letter D for diamond glide. So we have different kind of glides. We have an M, which has no translation, but if we add translation, we end up with the A, B, C, and diagonal or diamond glides that are notated in this way. The way that would work in terms of the point group symbols that we've seen, if you had something like 2 over M, That mirror would just be a simple reflection, no translation. Instead, if you had translation, though, along the c-axis, then it would be a C glide, and so the 2m becomes a 2c. Or if we had this point group, let's say we had a 4 over m bar 3, 2 over m. We could have the case where, let's say, that mirror plane here becomes a diagonal glide. And so we would have a 4 over m bar 3, 2 over n instead of an m. And I think in this case, this particular space group would actually have a 4 sub 2. So if you go back and take a look at screw axes, in this case where you'd have a diamond glide, I think you'd have the case where you'd also have a certain amount of translation required along this 4-fold rotational axis. Anyway, those are the glides, A, B, C, D, and M.